But that is not always the case. There are some equations, it's just too complicated to actually solve the solutions of, sometimes it's very simple, but it's very difficult to find the solutions to, right? For instance, I'm going to give you a couple of examples here. That for the populations model, we briefly talked about this the first lecture, that you have the exponential growth to be dp/dt equal to r times p, right? If you use separation of variable, you can solve these equations, and the result should be a exponential functions, right? P of t will be related to exponential functions. If you add more terms here, if you have 1 minus p over k, well, k is the carrying capacity. This is called the logistic growth, because when you solve the solution, you get the solution when you analyze that. You let t go to infinity, or you take the limit of the solution as t go to infinity, the solutions approach the value k. Right? So that's why it's the threshold or the carrying capacity. So no matter how much the population grows, it has to cap up at that level. If the system want to get out of that level, some people have to get away from the area of considerations. The example is the elevator, the capacity, let's say, is 100 people. You cannot get over 100 people. 100 people is the carrying capacity. Okay? If you want to get another person into the elevator, then one person inside the elevator has to get out. Okay. So again, this is the logistic growth. Then there's another called P over A. Sorry, P over T minus 1. Okay, so this is called the threshold plus logistic growth. This is the exponential growth is easy to solve, even though it might take you like 10 minutes or 15 minutes to solve it. The logistic growth would take you probably a good 20 minutes to 25 minutes if you know the math well enough. But for this one, this is there's the name for that. It's called the alley effect. It's just impossible to solve for solution analytically, right? But we still be able to understand this particular differential equations because it's the name of that is logistic growth plus the threshold model. So with the threshold and the carrying capacity, is say that. So this is the axis P, this is the axis P, this is the threshold, this is the carrying capacity. If the populations get below the threshold, the population eventually will die down. Okay. If the population get above the threshold, the population will act as logistic growth. If the population get above the carrying capacity, the population will act as the exponential growth. Okay, so by looking at this particular differential equations, the alley effect, we still be able to analyze the behavior of the solutions curves, even though that is really difficult to solve the solutions analytically. Okay, so that is the idea of this lecture about the solution curves and direction fields, because there are some differential equations that we cannot find the solution to or invent a method to solve the solutions analytically. Right. However, when you look at differential equation itself, it can sometimes tell you the specifics on how the solutions behave. Right. Well, and when you have this type of problem, you can ask yourself the two questions. How does the solution behave near a certain point? Right? A certain point here means that if given an initial condition, how is that going to behave? For example, if you look at this graph again on the alley effect, if the initial condition is right here, below the threshold, then the solution will lead you to extension. Okay. If you have a initial point right there, the initial point or the solution curve will lead you to logistic growth. That means the solution or the population will eventually get into the carrying capacity. If you get here, right here, the initial point, then the solution behaves like the exponential functions, right? Or the population will increase exponentially. Right? And so not only you want to know the behavior of solution near the initial condition or the initial point or any point for that matter, then you can do that analysis. In addition to that, you also want to know the end behavior of the solutions. That is, when you let x go to infinity or you let the independent variable go to infinity, what happened to the solutions? Okay, so that, and to understand the directions field and look at the solution curve and how to analyze the direction field and the solution curve, we need to go over some concepts. Some of this you may have seen in the past already in Calculus 1 and Calculus 2, more specifically in Calculus 1. Okay. So when you take differential equations, let me talk about derivative. Right? Derivative on one side, some function on the other side, as in the setup of this particular differential equations right here, dy dx equal to f of x comma y. Right? So a derivative dy dx of a differentiable functions y of x. When you solve for these equations, then you have the solution y of x. And this dy dx gives the slope of the tangent line at point on the graph of the functions. Right? So here you have some graph. Right? So here it's just a point, a linear segment at a point, like going through a point. Nothing fancy there. So line segment through a point. But with this line segment, you know the slope. And this slope will correspond to the tangent line that tangent to the solution curve of the differential equation of considerations. So this one is the line segment. Line segment is tangent to a solution curve. That passes through a point. Okay. So that's how you actually graph the differential equation, or more specifically, the direction field of the differential equations. So if we symptomatically evaluate f over a rectangular grid of points in the xy plane and draw a line element at each point xy of the grid with the slope f of x comma y, because of the equations we look at is dy dx equal to f of x comma y. So dy dx is the slope, therefore f of x comma y is also the slope. Then the collection of these line elements is called a direction field, or a slope field of direction of differential equations of the form dy dx equal to f of x comma y. So the graph of this direction field is very simple, similar to how you graph an equation of a line or how you graph an equation of a parabola. You make a table, right? On one side, if you want to graph, let's say, this is a sine node, you want to graph this equation y equal to x. What you normally do is you make a table. On one side, you have x, which is independent variable. The other side, you have y, which is dependent variable. And then you just plug in on like some random point, and then plot the graph of the line y equal to x. Similar to that, when you have a differential equation, you also make a table where you plug in some random numbers, and then depends on the value of x and y, then you have the different value for dy dx. For example, if you want to graph this differential equations, right? So let's say xy. Then on the right hand side, you have the value of x and y multiplied together. So if you make a table, right? So this is x, y, and then dy dx. Okay. So let's say you have 1, 1. Right? So x times y is equal to 1. What does that mean? It means that the slope is equal to 1. That is a positive slope. Right? So therefore, on the graph at the point 1, 1, 1, 1, you just put a little line segment like this, right, pointing upward, that indicate that that is the positive slope. Now, if you go to another point on the graph, you do -1, +1, then you have negative slope. Right? You go to that point, you draw a little line, and then you have a negative slope, right, pointing slanting downward. Right. So that is how you draw a direction field. I'm not going to spend too much time on, specifically spend time on drawing direction field. Eventually, you will know how to do the analysis of all of this. So in a way, right, to graph the direction field of the differential equation is very similar to how you graph a line, a straight line, or a parabola, or a cubic function, or any function for that matter. Right, so visually, direction field suggests the appearance or shape of a family of solution curves of differential equations. Right, it just gives you a visual understanding on how the solution curves behave. A single solution curve that passes through a direction field must follow the flow pattern of the field. Okay, so in the next page, I'm going to give you some example. Like on one side is the direction field, and on the other side is the corresponding solution curves. And again, the solution curves has to follow the pattern of the direction field. Okay. Example 1, direction fields and solution curves of some differential equations. So on the first graph right here, this is the direction field for dy dx equal to x squared minus y. Now assume that for some reason I asked you to draw the direction field of this particular differential equation. Again, how would you do that? You make a little table, right? You have three different columns, x, y, and dy dx. Right? So let's try a few values and see what happens. Right? For the value x equal to 0, okay, actually let me draw out the table. You don't have to write it down. Just for demonstrations, x, y, and dy dx. Let's say you have x equal to 0, y equal to 0. Therefore, 0 squared minus 0 is 0. Right? So it's just flat. It's just 0. Right? There's nothing there. So when you zoom in to this graph, you can see this right here. It's just a flat line to indicate that the slope is equal to 0. Right? Or you have something called the horizontal tangent line. Or if you consider this point right here, x equal to 0, y equal to positive 1, x equal to 0, y equal to positive 1, then dy dx is 0 minus 1. Right? That is a negative slope. So therefore, this point right here, at this point, you have the slope look like this. It's sliding down a little bit, pointing downward from left to right, indicate that that is the negative slope. And you do this for a bunch of points on the xy plane. Now, on the right-hand side, you have the solution curve to the same differential equation. The solution curves of dy dx equal to x squared minus y. Right. Now, all of this direction field gives you some suggestions on how the solutions curve is going to behave. Right? If you look at the solution curve in blue, it's follow the direction field. So moving on to the second set of graphs, you have on the left is the direction field. For dy dx equal to negative 2y. And on the right is the solution, a solution curve of dy dx equal to negative 2y. Because you have infinitely many points on the plan, on the xy plan, so there should be infinitely many little dashed line like this in the direction fields. Right? Here, it just gives you some idea of how the directions field is going to behave. And the last set of graphs. So this is directions field for dy dx equal to negative y over x. And on the right is the solution curve of dy dx equal to negative y over x. And as you can see here, you have x in the denominator. So therefore, at the origin, you can see the direction fields kind of like moving away from the origins, right? Because the origin is undefined in this case. So these calculations that we have earlier is for different value of x and y. You can have a different value of the slope dy dx. And of course, we always consider three cases for the slope when you have when the slope is positive, when the slope is negative, and when the slope is equal to 0 or the derivative is equal to 0, what's going to happen? Now go back to calculus 1. When you have the derivative to be equal to be a positive number, so dy dx is greater than 0, then the solutions when you solve has to be, or the functions or the dependent variable has to be increasing functions. Then y of x is increasing. When you have dy dx to be less than 0, y of x is decreasing. And when dy dx is equal to 0, you have something very interesting happen. That is, you can find something called critical points. And that is very essential for toward our analysis for differential equations. So an ordinary differential equation in which the independent variable does not appear explicitly, right, is said to be autonomous. If the symbol actually know the independent variable, then autonomous first order differential equations can be written as this form or the normal form of this. Right? So the right-hand side now is only the function depends on the dependent variable. There's no independent variable. I'm going to give you two examples. One is with autonomous equation, and the other one is non-autonomous equations. All right, so let's consider the following first-order differential equations. You have dy dx equal to 1 plus y squared. This is just the function depends on y only, and there's no independent variable. So this particular equation is called the autonomous equation. If you have a differential equation of the form x times y, this is the, on the right-hand side is the function of both x and y, both independent variable and dependent variable. So therefore, you conclude that this is a non-autonomous equation. With autonomous differential equations, is again help us identify critical point. So a real number c is the critical point of the autonomous differential equation of this form. Again, the right-hand side of autonomous equation is with no independent variable. Okay, if it is a zero of f, that is, if you have a critical number, you substitute into the function f of y, then you get the solutions to be equal to zero. So f of c equal to zero. Another name for critical point is called the equilibrium point or stationary point, and that point is very important for our analysis. Now, if C is a critical point of the autonomous system, then the constant solution f of x, y of x equal to C then y of x equal to C is a constant solution. And the constant solution is also called the equilibrium solution. Okay, so that's just some terminology that we need to get familiar with or know how to pronounce. Moving on to example 3. So in this example, again, you see that it's related to logistic growth. We're not going to solve this analytically. Right? You could, right, using separations of variable, but for our example in this lecture, we're just going to analyze this using the critical points and the idea of the derivatives, derivative positive, negative, or equal to zero. All right. So let me quickly note that this is the logistic growth. All right. Now, to find the critical number, or to determine the critical number, or critical point, we set the PDT equal to 0. Yeah. So that is you have P times A minus BP equal to 0. Therefore, you're going to have two critical numbers, so two critical points. One is that of P equal to 0, and P is equal to A over B. Now, again, I'm talking about logistic growth. That means something related to populations. You get two critical numbers or two critical points. You put this on the real line, or in this case, the p-axis, the axis of the population. And this is the graph of the p-axis with two critical numbers, 0 and A over P. Obviously, A over P is a positive number. I just want to be sure here, A over B is a positive number. Now, at the same time, when you see the graph, you see three little arrows here. What's going to happen? So those are the indicators that the behavior of the solution along the p-axis. All right, because when you put these two critical points on the p-axis, you break down into three different intervals, from negative infinity to 0, from 0 to A over B, and from A over B to positive infinity. You follow that idea? All right, so we're going to analyze that. So I'm going to make a little table here. The first column is for the interval. The second column is the sign of f of p, given that here f of b. I'm going to rewrite this dp dt equal to p times little b. So I'm inside the parenthesis, I'm going to take a little b out as a common factor, and I'm left with a over b minus p. And the right-hand side is f of p. Right? The reason I pull out a little b, because for convenience of calculations, you will see in a minute. The last column in our table is P of t. Right? So the last column here is going to tell you the behavior of the solution. Now, as I mentioned, I have three intervals on this p-axis, from negative infinity to 0, from 0 to A over B, and from A over B to positive infinity. Now, for each interval, you want to know the sign of the right-hand side of the differential equations. Right? So you want to know the sign of this term right here, the right-hand side. Okay. So in the interval from negative infinity to 0, that means p is less than 0. Less than 0, so negative times positive become negative. So these two terms combined together give you negative. You with me on that? right? Now for this term, a over b minus some negative number, right? So minus negative become positive. So this term is positive. So positive, positive, negative. So therefore, in the interval between negative infinity to 0, the sign of f of p is negative. Because the sign of f of p is negative, so therefore the function p of t is decreasing. And hence the arrow pointing down or pointing away from 0, downward, right here. Now in the second interval between 0 and a over b, right? So between 0 and a over b, you have something that is positive but less than a over b, right? So positive, right? So this is positive, positive. So a over b minus p. Remember, p is something positive but less than a over b. So this term is positive. You agree with me on that? Okay. So altogether, the sign of f of p is positive in this interval. Because it's positive, the behavior of the solution has to be increasing. Hence, the arrow pointing away from 0 and toward a over b, or the last interval right here. You have p greater than a over p, right? Or the interval from a over b to positive infinity. Again, p is greater than a over b. So this is positive, positive. Remember, p is greater than a over b, so this term is negative. Right? So therefore, altogether, the sign of f of p is negative. Therefore, this is decreasing. Okay. Because it's decreasing, you have the arrow pointing downward toward a over b. Okay. So that is the analysis that you can have. Like, again, it's not going to give you the analytical solutions, but give you the idea on how the solution is going to behave over a period of time. Okay. And normally, this particular graph is called the phase portrait or phase plan. Right? And the analysis we just done, that is called the phase plan analysis. So here, quick note, this is called the, so this one is one-dimensional phase portrait. Right, so now you have the phase plan analysis done. Gonna compare that with the solution curves that can create based on the phase plan of the phase plan that we just analyzed. So for this second pictures here, this is the phase plan and the solution curves. Again, when you look at the differential equations, we analyze that we obtain two critical numbers or two critical points, p equal to 0 and p equal to a over b. And now from that, we say that the two critical points break the line into three different parts, or it's give you three different intervals. Or in this case, for the solution curve, it's give you three different regions of consideration. The first region is region 3, region 1. Let's start with region 1. This is the case when p is less than 0. Region 2 is when p is between 0 and a over b. And region 3 is when p is greater than a over b. So it's tell you here from our analysis that the function or p of t is decreasing, right? Decreasing to actually negative infinity, right? So such as from this solution curve. Okay. So when you take the limit of the function p of t as t equal to positive infinity, if you let the system run over time, then this is what you have. Right? So p of t will approach negative infinity as t equal to positive infinity. Now, in the second region between 0 and a over p, when you take the limit of p of t as t go to infinity, you have that the solution approaches a over b, which is the carrying capacity. And when p is greater than a over b, when you take the limit of the functions as p go to infinity, you see that it also get down to or approaches a over b, which is the carrying capacity. And from this graph right here, it's again tell you a lot of things, not only the solution behavior of the solution, but also the stability of the critical points of considerations. When you have 2 critical points right here, right? And for this point, the two arrows pointing toward the point. When you have all of the arrows pointing toward a point, that point is considered a stable, or mathematically is called asymptotically stable point. Asymptotically because you have to take limits, right? It's not really just stable, it's not asymptotically stable. When you have a point where the two arrows pointing away from the point is considered unstable. If you have a critical point where one side is moving away and one side moving toward the point, then that point is called the semi-stable point. You with me on that? Okay, so that leads us to the next topic, is attractors and repellers. Okay. Now suppose that you have y of x is a non-constant solutions of the autonomous differential equations. Can you fix this one? This should be f of y instead of f of x comma y, because we're considering the autonomous system. Right. You have a non-constant solution to a autonomous differential equation, and C is the critical point of differential equations. Then you can classify the critical point using these three properties. Right? So for asymptotically stable, right, say that solutions tends to converge to the critical point as time approaches infinity. Now for unstable critical point or unstable point, the solutions tends to diverge away. So from the critical point as time approaches infinity. And the last type is called the semi-stable point. This is where solution converges on the one side and then diverges on the other side of the critical point. So that's just for autonomous differential equations. You can actually apply all of this idea into a non-autonomous differential equations. Okay, autonomous differential equation is simple enough for us to do the analysis. Okay, but the same analysis, similar analysis, can be applied for a non-autonomous system. Okay, before doing an example, 3 examples related to non-autonomous system, I'm going to take some note here. So you can see there are 4 different lines indicating a different meaning of the critical point. So for A, here's the critical point, and the arrow is pointing toward the critical point. So this part A is the point is asymptotically stable. For B, the arrow is pointing away from the critical numbers on the critical point. So this is unstable. Then for C and D, the solution converge on one side and diverge on the other side of the critical number. So therefore C and D are semi-stable.